Welcome to The Explainer. Today we're doing something a little bit different. We're actually going to explore the hidden mechanics behind this very presentation. We're unpacking the clash between probabilistic AI and deterministic hardware, and we're going to look at exactly why text is the ultimate, universal interface bridging those two worlds. To kick things off, we really just need to break the fourth wall for a second and ask a totally meta question. How is this exact explainer being generated right now? Like, are you experiencing a mere facsimile of intelligence that was just cooked up by a statistical engine? Or is there a rigid deterministic fidelity at play underneath the whole thing? To figure that out, we have to look at this fascinating conflict happening at the very core of modern computing. All right, let's dive into this massive divide. On one side, you have connectionist AI, large language models. They map human language into these messy, continuous vector spaces. They're totally opaque, they're probabilistic, and yeah, they definitely hallucinate. But then, on the other side, we have the strict, discrete mathematical reality of hardware arithmetic logic units, or ALUs. I mean, this is silicon. It's symbolic, it's verifiable, and it demands absolute exactness. Bringing these two completely opposite paradigms together, that is literally the central challenge of modern AI.
And this leads us straight into a phenomenon we call fax machine decay. Because LLMs act a lot like lossy zip files, they gorge themselves on hundreds of terabytes of data, but then they compress it. And because of that massive compression, they suffer from inherently stochastic, unpredictable outputs. Once they're trained, they don't truly recollect information the way human working memory does, right? Instead, they're just generating the next most probable word. They're a continuous approximation of knowledge. They're definitely not a database of exact facts.
Section 1. The ASCII Tokenization Bottleneck.
To really understand the friction between probabilistic AI and discrete computers, we've got to look at byte-pair encoding, or BPE. Before a neural network can even begin to process human language, it has to force our continuous associative thoughts through the super-narrow, lossy bottleneck. BPE is basically a frequency-based compression algorithm that scans text and iteratively merges the most frequent adjacent characters into discrete numerical IDs. It acts as a translation layer that discretizes continuous concepts just so the machine can actually read them. Now here's the kicker. This ASCII discretization creates some absolutely severe logical vulnerabilities. Because BPE operates on character frequencies, the word good with a lowercase g and the word good with a capital G get assigned completely distinct IDs. The model literally has to burn its internal capacity just to figure out they mean the exact same thing. Even a random trailing whitespace will alter token boundaries. And don't even get me started on math. The constant 3.1415 might just get arbitrarily chunked into a 3, a decimal point, a 14, and a 159. Because those boundaries don't align with decimal logic at all, the AI simply cannot learn systematic arithmetic, it just memorizes strings of numbers. This massively amplifies what researchers call the modality gap between continuous signals and discrete tokens.
Section 2. The illusion of memory.
All of these tokenization issues feed into that broader modality gap, a concept that Noam Chomsky captured perfectly. He reminds us of a really fundamental difference. Unlike the human mind, which, seeks to create explanations and operates with incredible efficiency, current large language models totally lack non-sequential planning. They operate purely as probabilistic pattern matchers. They don't have a gut feeling, and they certainly don't hold true working memory. They are really just inferring brute correlations.
Section 3. Text as semiotic bridge. Which brings us to the ultimate question. How do we actually connect the associative nature of human cognition with the rigid execution of the machine? Well, the answer is text. Text acts as the semiotic bridge. Specifically, strictly formatted text like JSON or Python scripts. It serves as the universal deterministic interface. Our collective symbolic cognition, what researchers sometimes call our fundamental human operating system, or OS alpha, uses imperative text scripts to direct the machine. Text is quite literally the only way to safely compile our associative imagination into exact hardware execution.
This idea is actually rooted super deeply in Charles Sanders Peirce's semiotic philosophy. By following his three-step progression of signs, starting with abstract representations, then moving to active representaments, and finally embedding them into material substrates like a microchip, human intelligence can be safely and predictably compiled right into the physical behavior of silicon processors. It's basically a formal symbolic grounding process.
Section 4. Enforcing strict ALU fidelity.
So how do we actually enforce this strict mathematical fidelity out in the real world?
We do it through frameworks like compiled AI and the yield protocol. Yield stands for yielding execution and instruction loading via delegation. Basically, when a system encounters a task that requires exact arithmetic or strict logic, it just pauses the probabilistic neural execution. It hands the state over to deterministic, mechanistic circuits using pre-tested text templates. This completely bounds the error space, so the model literally cannot hallucinate an incorrect API call or mess up a math equation.
This is beautifully grounded in reality through things like binary verification graphs. Take the CL4 operating system microkernel, for example. The process maps the mathematically verified refinement from high-level, abstract human text specifications all the way down to deterministic, assembly-level binary execution. It proves that yes, we absolutely can guarantee safety and functional correctness without relying on the probabilistic whims of an AI.
Section 5. Agentic tort and authorship.
As we step back, we really have to look at the physical world. If an AI makes a probabilistic mistake, we face what scholars call moral crumple zones. These are situations where responsibility gets completely obscured by the complexity of the machine, leaving humans to absorb the damage. And this makes it absolutely vital for you as a human developer to use deterministic text to assert agentic tort. This means legally and technically bridging the gap between your abstraction choices and foreseeable harms. You must intentionally author the constraints that bend the AI toward a moral, anti-destructive mandate.
In fact, to bring it all full circle, the very creation of this explainer series uses imperative JSON and Python scripts, something we actually call the sovereign gate. It's the physical manifestation of human intent asserting direct control over the probabilistic machine. The script acts as an interceptor. It forces the language model to align exactly with my intent as the human author, ensuring the ALU executes exactly what was designed, not just what happened to be statistically probable in the moment.
So I want to leave you with this final provocative thought to ponder. As we integrate these systems deeper and deeper into our lives, you are the steward of the machine. In a world increasingly run by massive, lossy statistical engines, will you actively use text to wield the divine script and build true deterministic fidelity? Or will you just settle for a mere facsimile of intelligence and let the probabilistic noise take control? The choice and the authorship is totally yours. Thanks for tuning into this explainer.